Hey everyone, and welcome to The Explainer. All right, let's jump straight in because today we are tackling something totally mind-bending. You know, when you step outside and look down at the ground, it feels completely solid, right? Like it's permanent and unmoving. But what if I told you that the seemingly solid ground beneath your feet is actually just one tiny piece of a massive, constantly moving geological machine?
It really boils down to one simple question, but it's a question that completely flips our perception of a static Earth upside down. Have the continents always been where they are today? Like, have they always looked exactly the way they do on a modern globe? Setting up this geographical mystery is exactly what we're going to explore. We're going to dive into the evidence, the wild theories, and the ultimate discoveries that proved, without a doubt, that our planet's surface is constantly on the move.
Okay, so let's get into it. Section 1. The Continental Drift Mystery. This whole puzzle actually kicked off way back in 1596. A mapmaker named Abraham Ortelius was looking at maps and noticed, hey, the coastlines kind of look like they fit together. But it wasn't until 1912 that a German meteorologist named Alfred Wegener stepped up with a really bold, comprehensive argument. He called it the Continental Drift Theory. Wegener argued that roughly 200 million years ago, all the continents were actually jammed together into one single massive supercontinent. He called it Pangaea, which literally means all Earth, and surrounding this giant landmass was one global mega-ocean called Panthalassa, meaning all water. Eventually, Pangaea split into two huge chunks, Laurasia up north and Gondwanaland down south, before finally splintering into the smaller continents we know today.
Moving right along to Section 2, Clues Across the Oceans.
Now, to convince the scientific community of this wild idea, Wegener knew he needed hard, physical proof. And wow, the sheer variety of evidence he pulled together was just staggering. It wasn't just that the coastlines fit together like puzzle pieces. He used radioactive dating to show that a belt of ancient, 2-billion-year-old rocks on the coast of Brazil perfectly matched rocks in Western Africa. Mind-blowing, right? He also found thick deposits of tillite, that sedimentary rock left behind by glaciers in places like India, Africa, Madagascar, Antarctica, and Australia, proving they all share the exact same glacial history. He even pointed out these incredibly rich deposits of placer gold right on the coast of Ghana and Africa. The kicker? There is absolutely no source rock for that gold in Ghana. The source rock is over in Brazil, which of course makes perfect sense if those two landmasses were once sitting side by side.
But honestly, the most compelling evidence he had might just be biological. Take a look at the Mesosaurus. This was a small, ancient reptile that lived in shallow, brackish water. Yet identical skeletons of the Mesosaurus have only been found in two places on the entire planet, South Africa and Brazil. Today, those spots are separated by 4,800 kilometers of deep ocean. I mean, seriously, how could a tiny freshwater reptile possibly swim thousands of kilometers across an ocean? Well, the logical conclusion was it didn't. The landmasses had to be physically connected.
So, Wegener had this incredible, undeniable evidence of movement. But there was a fatal flaw in his theory. When scientists asked him, okay, but what force on Earth could possibly push massive continents across the globe? Wegener suggested it was pole-fleeing forces from the Earth's rotation and tidal forces from the sun and moon. The scientific reality? Yeah, most scholars of his day took one look at that and correctly pointed out that those forces were entirely inadequate to move colossal continents. So unfortunately, his theory got shelved.
Which brings us to Section 3, Secrets of the Seafloor.
Fast forward a bit. After World War II, we started doing really detailed mapping of the ocean floor. And we found completely submerged mountain ranges, massive deep trenches, and active mid-oceanic ridges. But all this new data brought scientists right back to the million-dollar question that had stumped Wegener. What forces move solid rock? If the continents are actually moving, what the heck is the engine driving it?
Well, the answer was hiding deep beneath the crust. Way back in the 1930s, Arthur Holmes had actually proposed this idea of convection currents operating inside the Earth's mantle. You see, heat inside the Earth comes from two main sources: radioactive decay and leftover residual heat from the planet's formation. This intense heat causes the softened, semi-solid mantle material to rise up toward the surface, spread out, cool down, and then sink right back down into the depths. This slow, constant cycle creates what we call a convection cell. Think of it like a giant geological conveyor belt operating deep underground.
And that conveyor belt led straight to a massive revelation: 200 million. Post-World War II dating of oceanic rock revealed a literal smoking gun. It turns out the oceanic crust is surprisingly young. Like, nowhere on Earth is the ocean floor more than 200 million years old. To put that into perspective, some of the continental rocks we found date back an astounding 3.2 billion years.
Plus, the layer of sediment sitting on the ocean floor was unexpectedly thin. Something had to be wiping the slate clean.
This discovery of incredibly young ocean floors led Harry Hess in 1961 to propose a groundbreaking idea called seafloor spreading. He argued that constant volcanic eruptions at the crests of these mid-oceanic ridges actually cause the crust to rupture. New lava wedges into the crack, cools, and physically pushes the older ocean floor outwards on either side. But since the Earth isn't, inflating like a balloon, that spreading ocean floor eventually hits deep oceanic trenches where it sinks back down into the mantle and gets consumed. Basically, the ocean floor is a dynamic system constantly regenerating itself.
All right, on to Section 4, the Plate Tectonics Revolution.
With Hess's concept of seafloor spreading out there, interest in how continents move just exploded. It's like a scientific detective story that took centuries to solve. It started with Rutilius noticing those matching coastlines back in 1596, then Wegener's bold Continental Drift Theory in 1912, Holmes talking about mantle convection in the 30s, Hess dropping the seafloor spreading idea in 61, until finally in 1967, scientists put all these puzzle pieces together to formulate one grand, definitive breakthrough: plate tectonics.
So, what exactly is a tectonic plate, or a lithospheric plate? Simply put, it's a massive, irregularly shaped slab of solid rock. These colossal plates move horizontally over the softer, hotter layer below them, called the asthenosphere, as one rigid unit. The Earth's whole outer shell is actually cracked into 7 major plates and a bunch of minor ones. And right here is the absolutely crucial correction to Wegener's original theory. It is not the continents themselves drifting independently through the oceans. No, the continents are firmly embedded right into these larger plates. The continents are just coming along for the ride while the plate itself moves.
And because the entire surface of the Earth is paved with these giant moving puzzle pieces, they inevitably crash and interact in 3 main ways. First, at divergent boundaries, like the Mid-Atlantic Ridge, plates pull away from each other, generating brand new crust. Second, at convergent boundaries, one plate dives completely under another in what's called a subduction zone, and crust is actively destroyed. And third, at transform boundaries, the plates just kind of grind and slide horizontally past each other, meaning crust isn't produced or destroyed, just scraped up.
Nowadays, scientists can actually track exactly how fast these plates are moving, mainly by studying strips of magnetic fields on the ocean floor. And the difference in speeds is honestly wild. The Arctic Ridge is creeping along at the absolute slowest rate, less than 2.5 centimeters per year. Meanwhile, over at the East Pacific Rise, it's practically sprinting, at least in geological terms, moving at a super speedy rate of more than 15 centimeters per year.
Let's wrap this up with Section 5, the dramatic journey of India.
Let's take literally everything we just learned, the convection currents, the seafloor spreading, the tectonic plates, and apply it to an epic, real-world case study. Roughly 225 million years ago, India wasn't where it is today. It was actually a large island way down south near the Australian coast, separated from Asia by a massive body of water called the Tethys Sea. Then, around 200 million years ago, when Pangaea started breaking apart, India hit the gas on a massive northward journey. As it traveled, about 60 million years ago, an incredible outpouring of lava created what we called the Deccan Traps. Finally, 40 to 50 million years ago, India absolutely slammed into the Eurasian plate. And the result of that epic, slow-motion continent-to-continent crash? It caused the rapid, violent uplift of the Earth that formed the Himalayas. But here is the absolute coolest part. This is not just ancient history. Because plate tectonics is an active, ongoing machine powered by that intense heat deep inside the Earth, the Indian plate is literally still pushing into Eurasia right now. Scientists believe this convergence is happening as we speak, meaning the peaks of the Himalayan mountains are actively getting pushed higher and higher into the sky today. So, as we close out this explainer, I want to leave you with one final, kind of mind-blowing thought to ponder. If we know for a fact that the Earth's interior is this dynamic running engine, and that all tectonic plates, without exception, are currently moving and will absolutely keep moving into the future, where will the continents be in another 200 million years? Like, what will the map of our world even look like then? Thank you so much for exploring the dynamic, shifting surface of our amazing planet with me today. Keep asking questions and keep exploring.